Great. So excited to announce our next speaker is Stephen Flammia from AWS and Caltech, who will be telling us about average circuit eigenvalue sampling. Please take it away, Steve.
Thanks a lot. And I'm sorry that I couldn't be there in person. So yeah, I'm going to tell you about this paper I wrote last year called Averaged Circuit Eigenvalue Sampling. It's a really simple idea, but I believe that it's quite powerful. So this is a talk about learning noise in quantum devices. And of course, the general problem of learning noise is essential for improving our quantum devices, but it's also intractable, if only just because of the exponentially growing size of the Hilbert space. So if you want to solve this problem, you need to rephrase it to something that's a little more tractable. And one way to do that is to make structural assumptions about the noise. And I find that it's convenient to make a dichotomy into two types of noise. This isn't a real, don't take this too seriously because there are things that live in sort of both worlds, but it's helpful for me to conceptualize noise as falling into roughly two classes, coherent noise and incoherent noise. And coherent noise is roughly that which is generated by a Hamiltonian and is unitary. And you can learn this noise. You can learn Hamiltonians efficiently. So you can learn the difference between what Hamiltonian you were trying to build into your device versus the Hamiltonian that you were actually presented with the device you fabricated. But removing all of these Hamiltonian terms is in general quite hard and becomes impractical. And at some point, you need to stop trying to remove coherent noise and use quantum error correction to deal with what I'll call incoherent noise. So when I talk about incoherent noise, I will effectively only be talking about Pauli channels, although I can incorporate erasure channels, loss channels into this as well. So when I say incoherent noise, I really am going to mean stochastic Pauli noise, which I'll define on the next slide. But basically, why am I going to focus on this? Well, because like I just said, when your calibration stage is over with a device, you can't effectively deal with coherent noise anymore. But you can learn Pauli noise, and we know from several studies about biased noise that biased noise can dramatically increase the threshold for quantum error correction. There are also tools such as dynamical decoupling, Pauli frame randomization, randomized compiling, etc., that can enforce a Pauli approximation. So if your noise isn't exactly a Pauli channel, but you've given up on removing coherent noise, then you can project your noise without loss of fidelity to be of the form of a Pauli channel. Also, quantum error correction seems to make noise incoherent. So if you're doing this at the logical level, this is a very good approximation. And lastly, Pauli noise can be compensated for quite effectively using error mitigation techniques. So these are all good reasons to focus on the class of Pauli channels. So there's a huge amount of literature on estimating incoherent noise, usually not estimating a full Pauli channel, usually estimating some coarse statistic of a channel, such as the average gate fidelity. Most of these methods have the word benchmarking somewhere in their name. The most famous of these is randomized benchmarking, but there are a bunch of intellectually descendant techniques. And this in some ways falls in that same category, but it's much more general, as you'll see. So this, what I'll talk about today is really, it unifies a lot of these. I mean, there have been several papers that say we unify these into a common framework. I don't think that all of those are particularly useful, those frameworks. I don't know if this one's more useful, but I hope that it's quite useful. And what mine does that these don't is it gives specific information about individual gates. And the only one on here that does that is interleaved benchmarking. And I'll hope to convince you that there are some big advantages compared to interleaved benchmarking. So let me define what a Pauli channel is. So a Pauli channel is just a stochastic quantum channel. It's a channel where the Krauss operators are Pauli operators in some convex combination. So P is just a probability distribution over Pauli errors. And we will call this the Pauli error rates. And there are 4 to the n Pauli error rates. Sorry, I have a dog that if I let him out, he's gonna wake up the girls. Okay, sorry. The Pauli operators, the important thing to know about the Pauli operators is that, of course, they don't commute, but they do commute up to some phase. Okay, and it's not so important how you compute this phase. Probably everybody in the audience has had to do this at some point, and I like this notation here to describe whether or not the Pauli labeled X and the Pauli labeled Y commute up to this phase. Okay. There's another important notion that comes with Pauli error rates, which is what I call the Pauli eigenvalues, lambda. Okay, and so if you tell me this list, this vector of Pauli error rates, then I can compute this quantity, which is just a linear combination of these Pauli error rates with these signs weighted by whether or not it commutes or anti-commutes with this label Y for another Pauli. And this sum here gives me the Pauli eigenvalue. Why is this the eigenvalue? Well, it's the eigenvalue because if I take a Pauli channel E, so I should have said E is my Pauli channel, and I act it on, it's a linear operator, so I don't have to act it on a state. I can act it on any matrix I like. If I act it on the Pauli PY, and then I apply this sign relation, and I use the fact that the Pauli is square to the identity, I find that the Pauli channel acting on Pauli p sub y gives me back p sub y times this factor, lambda sub y. So this is indeed the eigenvalue of the noisy Pauli channel whose Pauli error rates are px. This is the eigenvalue with respect to the eigenvector py, the Pauli py. Okay, therefore, Pauli operators are the eigenvectors of Pauli channels, and Pauli channel superoperators are diagonal in the Pauli basis. So therefore, the relation between, this is an invertible relationship as well. So there's an inverse transform that looks like this. So if I know the Pauli error rates, I can compute the Pauli eigenvalues and vice versa. This is it's up to an overall scale factor as a unitary transform. So this is sort of lossless from a precision perspective in L2. Okay, so we can identify, and actually maybe I'll just mention very briefly that this idea of projecting noise into the Pauli basis works really well in practice. What you do is you just take your circuit and you insert random Pauli operators everywhere, basically, and you compensate for this. And when you do this, this is a depiction, this is from an experiment in a transmon system. And this is a picture of the diagonal superoperator representation in the Pauli basis. Sorry, the superoperator representation where the diagonals are the Pauli eigenvalues. But this is a general channel, as you can see from the existence of these off-diagonal elements. It's not diagonal in the Pauli basis, so it's not a Pauli channel. But after they average over the Pauli group, they do some group averaging, they can kill these off-diagonal elements, and the fidelity is the same. Why do I know that the fidelity is the same? Because there's a formula that the trace of this superoperator divided by 4 actually is the fidelity. And you can just tell that the diagonal elements are basically unchanged from this operation. So therefore, I can project noise channels into Pauli channels losslessly in the sense that the fidelity is preserved under this action. So therefore, I claim we can just think about Pauli channels. Okay, everyone here knows what the Clifford group is. The most important fact is that if I act with a Clifford gate, so I've slightly overloaded my notation here for G acts in this way by conjugation. So if I say G of P of X, it means G Px G dagger. It will map it to some new Pauli, possibly times some plus or minus sign. These plus or minus signs are important to monitor in practice, but everything that I'm going to talk about in this talk is insensitive to how these signs play out in the end. So in order to save myself and you any headaches, I'm going to completely ignore these plus or minus signs that come out under Clifford conjugation. Okay, they're there, you have to deal with them. They're annoying, you can deal with them. We're going to ignore them from now on. That said, if you have a question about them at the end, please don't hesitate to ask. Okay, so now I'm going to step into the scenario where we're going to apply this ACEs method. So suppose that I have a quantum circuit composed of a bunch of Clifford gates, G sub k. And suppose that for each one, we associate a Pauli noise channel E sub k. So this is the kth gate in some circuit, and it has some Pauli noise ek. Okay, I can actually just define this guy in terms of the sort of pullback. I can multiply by GK dagger and define the noise to be the residual noise on my noisy gate compared to the ideal gate. So you can think of this as being a definition of the noise that I'm trying to learn. And suppose further that I'm going to allow noise on state preparation and measurements. And our goal is to learn a description of all of this noise to some precision epsilon. And I'll be a little bit vague about this for the sake of time. But basically, ACES does this. So we can learn all of the noisy channel eigenvalues for each of these, assuming each of these Clifford gates has some constant size. So these are, C0 gates or something that has some, it's not, an N local gate, it's a K local gate for some constant K. Then I can learn all the Pauli eigenvalues of these noise channels to some fixed precision. I can do this using a small number of randomly chosen Clifford circuits. Like I will show numerics at the end where I can learn a 100 qubit system with like 20 Clifford circuits. And I can do all this with a polynomial number of samples in both the precision and the number of qubits. And the classical resources you'll see are polynomial. Okay, so I described already briefly how we average quantum circuits. Oops, oh no. Right, so averaging circuits just means I do the following. I pick a sort of outline for my circuit where I isolate a collection of gates. In this example taken from this paper by Wallman and Emerson, I have a circuit with a bunch of C0 gates in it. And at every intermediate time step, I'm going to insert random Pauli operators. Okay, remember these are all Clifford circuits. And then what I'm going to do is I'm going to follow their protocol called randomized compiling. I'm going to split this Pauli into a product of random Paulis that multiply to this same one, but that are correlated across this gate. And then I'm going to recompile it. And when I run my circuits, I'm going to sample from this ensemble. In expectation, this ensemble averages the noise on all of these intermediate gates over the Pauli group. And when I do this, I can implement this Pauli projection that I described on the earlier slide where I showed from this experiment the diagonal superoperator that resulted after the averaging. So when I do this, when I say a circuit, I really mean I'm sampling from this ensemble of circuits, okay? And I'm going to use this technique throughout. And they showed numerically in this paper and in subsequent papers that just a small number of averages, a constant number of averages like 10 or I think they say 12 or something, very quickly projects circuits into Pauli noise or effectively Pauli noise. Okay, so that's the averaged circuits part of this talk. Sorry. So given the general Clifford circuit now, so now I'm going to compose my circuit of a bunch of, these are the ideal gates. So C is my circuit, G1, 2 through T are the ideal gates comprised, that are composed to make the circuit. And the noisy gates, which I would normally put a little tilde on these guys, each one of them by this Pauli twirling technique is of the form some Pauli noise channel followed by an ideal Clifford gate and so on, okay? So using this average circuits method, randomized compiling, Pauli frame randomization, whatever you want to call it, I can always write my circuit in this standard form, okay? And I realize I should have put like preparation and a measurement here at the beginning in it. Okay, and let's suppose for the moment that this circuit is the identity, and let's analyze what happens. What are the eigenvalues and eigenvectors of this noisy superoperator? Well, we've seen that there's really only a couple things that can happen. The Pauli channel will take any input Pauli operator and multiply it by a constant, namely the Pauli eigenvalue of that channel. And we've also seen that the way the Cliffords act on Paulis is that it will permute those Paulis modulo some sign, which I said we were ignoring anyway. So the only thing that every element in this product can do is either multiply by a factor or permute. So this product effectively preserves this eigensystem. It changes the eigenvalues and it permutes the eigenvectors. That's the only thing that this circuit can do to a Pauli at the input. So therefore, I claim, moreover, that at the end of sending a Pauli through this circuit, because each individual circuit gate is producting up to equal the identity, then an input Pauli will get mapped back to itself times a factor. So therefore, this noisy channel is in fact a Pauli channel. Okay, it's a funny one that has some decomposition, but it's in fact a Pauli channel. And so it therefore has some Pauli eigenvalue, which I'll call, if I input Pauli X to this channel, I'll get back some Pauli eigenvalue, capital lambda X, okay? And I will call this the circuit eigenvalue. Okay. So now I've established that this is true if this total circuit is the identity. What is the relationship between the circuit eigenvalue and the individual eigenvalues here? Well, it's roughly that it's going to be a product in some way, but each product is going to get twisted by these individual permutations that interleave the Pauli channels. So let's see how this works. I'm going to inductively track how the Paulis permute when they go through this circuit. So if my input Pauli is Px1, then when I hit it with the ideal gate G1, I'm going to define the output to be Px2, okay? And similarly, if I feed in Pxk into the gate Gk, then I'm gonna get Pauli Pxk plus 1, okay? So now when I do this, each time I go through this noisy guy, I pick up an eigenvalue for the Pauli that's input here. This guy's gonna hit that Pauli and permute it to a new Pauli, and the pattern is just going to repeat, okay? So at the end of this, I'm just picking up Paulis, I'm bouncing each Pauli through this circuit. It picks up a factor here, and then it permutes, and its index increments by 1, and we repeat until we hit the end of the circuit. This factor is associated to this gate and the Pauli that gets input into that factor. Okay, so each one of these this circuit eigenvalue says, I just take this product. Oh, I probably should have written it the other way. And it's the first gate and the first input Pauli, and it's the eigenvalue of that Pauli for that gate. And then that is the second Pauli input into the second gate, and there's an eigenvalue for that, and so on, and it's just this product. Okay, if C is not the identity, the situation is very similar, except now we have a permutation. There's a net permutation at the end. So we can study this problem in the context of what's called a generalized eigenvalue or a generalized eigenvector, which is to say that we've permuted this index up to some overall permutation matrix B. So we've twisted the output Pauli, but otherwise it's roughly the same. So now the generalized eigenspectrum, meaning we allow that the Pauli got permuted, some net permutation at the end. Oh, this should have like a Y on it or something. This is for the identity case, the way this algebra is written, sorry. So we want to now, we can imagine feeding in, we'd like to study this set of equations, okay? Let's put that on hold for a minute and say, how do we actually estimate the circuit level eigenvalues, okay? Because now we have a way to relate all of the noise on the individual gates to something that we might be able to measure at the output of the circuit. So how do we do that? Well, we can't actually prepare a state P. P is not a state, so I can't put a state into a channel, put a Pauli operator into a channel, but I can put a stabilizer state into a channel, and I can analyze what happens to the Pauli part of the block vector for that stabilizer state. So the expected value of Pauli x sub t, that is the output Pauli at the end of this circuit, with respect to, so this is like the notation, this notation means, oh, it's written right here, yeah. You know, I'm using this notation to mean the trace of rho times the observable O. So if I were to compute this expectation as if this were a real state, this is, I twist this Pauli by this circuit, I pick up the circuit eigenvalue times the output Pauli, Pxt. The Paulis are an orthonormal basis in the operator space, so I just get this circuit fidelity, okay? So although Px is not a state, I can prepare states that look like this, right? I can prepare I plus P or I minus P, okay? And I can send that through the channel. And when I do that, I'm going to get, instead, I'm going to get output probabilities from this experiment that look like this: 1 plus or minus lambda x over 2. And more generally, I can do this for like a pure stabilizer state. If I difference these outputs, right? If I just look at the difference of the probabilities between the plus outcomes and the minus outcomes, then this offset cancels and I can isolate exactly this circuit eigenvalue. And this gives me, therefore, if I take samples and I take the empirical estimate at the output, I can learn this circuit eigenvalue. Okay, so any circuit eigenvalue of a Pauli that has constant weight, I can estimate the output probability distribution with a constant number of samples. And then I can use this differencing trick to estimate the circuit eigenvalue. Okay, so that's eigenvalue sampling. And now we're going to just put these pieces together. Okay, so what is ACEs? And I still have maybe a couple of minutes, so I'll go through this quick. ACEs is, I'm just going to do this for a bunch of random circuits and some inputs. So I freeze a circuit and I throw in a bunch of input states. It turns out I can analyze a bunch of input states in parallel with this method. And I'm going to define a bunch of model parameters. These could be Pauli noise parameters to define each of the elementary gates that are in this circuit. I can model correlations between gates in this way as well. For example, I don't have to consider H1 Hadamard on the first qubit and Hadamard on the second qubit as the only gates in the circuit. I can introduce a new gate called H1 tensor H2 and estimate the Pauli noise of H1 tensor H2 independently from H1 and H2. And therefore, I can track crosstalk between gates as well through this method. So heuristically, once the number of experimental parameters, that is the number of independent circuits and the number of inputs that I'm tracking, is larger than the number of model parameters, then the model should be identifiable. So how does this work? So each of the Pauli error rates for the individual gates is related by these two equations. The Pauli channel eigenvalues, I'm going to change variables. Remember, we had this product expression. So I'm going to transform to exponential variables, okay? And as long as your noise is close to the identity, each of these eigenvalues will be a positive number. So therefore, I can take logarithms, okay? That's what I'm going to do. So all of these equations were of the form like this. If your noise is close to the identity, I can take logs and there's no problem. So I'm going to estimate the circuit eigenvalues and take the log, and I'm going to define that to be B. And in these logarithmic coordinates, these noise parameters just add up linearly. So the entire problem boils down to solving AX equals B, okay? We just identify our model by solving AX equals B, and that gives me the eigenvalues, which gives me the Pauli error rates, just by each of these steps is invertible. Okay, so this is a numerical example. So I simulated n equals 100, so n 100 qubits in a 1D architecture where I can do CNOT gates between nearest neighbors, as well as the 6 different Cliffords that you get modulo Paulis. And then I sampled 20 Clifford circuits. So this model, if I assign independent Pauli noise to each one of these elements, there are 900 gates in this model and 5,000 model parameters. So you get an extremely rich and detailed picture of the individual noise on each of these individual gates, if you can learn all 5,000 of these parameters. So then I sampled the circuit level eigenvalues, 10 to the 4, 10 to the 5, 10 to the 6 times for each circuit. So 20 circuits, 1,000,000 shots each. If this is a superconducting architecture and you have sort of tens or hundreds of nanoseconds gate times, this is about a few minutes worth of experiment time that we're talking. So it's very feasible. So then I sampled 20 random circuits of varying circuit depth between about 2 and 89. Most of the circuits were shallow, and then I did a few longer circuits to isolate the measurement noise. So you can see, whoops, hold on. So this is the distribution of circuit eigenvalue estimates. This is a histogram across all the experiments, depending on how many samples I took. How does that translate into the accuracy of learning the gate parameters? Well, if I look at the total variation distance, the one norm distance between the Pali error rates on the jth gate, this is in units of percent, then already for 10 to the 4, I can learn every single gate to less than 1% error in total variation distance just by doing 10 to the 4 samples for 20 different circuits. If you grant me 1 million measurements, then this error rate drops down to about, like almost everyone is, most of them are within 0.1% in total variation distance. So this is very high accuracy. Just to wrap up, so the assumptions that go into this is that the Pali twirl is exact. Otherwise, I'm learning the noise averaged over this set. So in the paper that's online, I don't have a theorem that guarantees the sample complexity, but there's a paper that will come out on the archive soon, which will quantify this. But from what's in the paper, you can say like a differential analysis suggests that the sample complexity should depend on the condition number of this A matrix. Remember, we solved AX equals B. And 1 over epsilon squared, you always get this sort of sampling penalty times the number of circuits, which should be constant. So I'm going to wrap up some future directions. So some future directions is doing an online algorithm. So this is work in progress, but an online algorithm can track the error ellipse in real time, and you can do fast rank 1 updates and down dates to do error dependent noise. This is like a 3D slice of how the error ellipse converges to the true distribution. So I think this is something where we'll be able to do this quite fast as well by taking advantage of an online streaming algorithm version of ACEs. You might also ask, how do we optimize the design matrix, this A matrix, so that we can optimally collect data? And how do we go beyond Clifford circuits? So this will be, I have a paper coming up soon with Robert Huang and John Preskill, where we actually do a bigger, it's a bigger paper actually than just going beyond Clifford circuits. It's really about foundations for quantum learning. And that'll hopefully be on the archive this month. And of course, doing this in real experiments, I think, is a great open challenge. So thank you for your attention. I hope people are clapping because I can't hear anything. Good, thanks.
Thanks very much. That's very interesting. I guess there's time for a couple of questions.
You're going to have to repeat the questions, Ryan, because I apparently cannot hear the audience.
Okay, well, Ashley.
Okay. So first, thanks very much, Steve, for a very nice talk and joining us so early. I don't know if you can hear that, but thank you. So I guess my question was, are you always assuming in your model that every gate in the circuit has sort of different error parameters somehow? So like you do a gate on qubits 1 and 2 at time 2 is looking very different to a gate on 2 at time 10. Or
sorry. Yeah, I was running out of time at the end, and I should have said that the noise is sort of time homogeneous. So it's like what people studying time series call wide sense stationary, meaning that the noise on each gate at time t is time translation invariant. So I don't allow arbitrary time dependence. You can allow some limited time dependence, but it's a little bit artificial. So if I do gate 1 at time 1 and I do the same gate at time 50, it's the same noise. It's the same noise distribution. The noise is sampled from the same distribution at each time. Yeah, thanks.
Any other questions? If not, let's thank Steve again.